Welcome to this second session of today, dedicated to knowledge representation and learning. We will have 3 talks in this session. The first one is about ad hoc teamwork, that is the problem of enabling an agent to collaborate with others without any prior coordination. It is a work by Hasra Dodampegama and Mohan from University of Edinburgh, and Hasra is going to present us the work. The title is Knowledge-Based Reasoning and Learning in Ad hoc Teamwork. Thank you, Hasra.
Thank you. Thank you. So today, is it okay? Okay. Yes. I think it's fine. Okay. So So I will talk about an architecture for ad hoc teamwork which combines knowledge-based reasoning and data-driven learning. And the focus will be mostly on the explanation generation and the knowledge acquisition part. So if I talk a little bit about ad hoc teamwork, we talk about collaboration of agents without prior coordination. So for example, here we have these 2 domains. The first one is fort attack, where you have a team of guards trying to protect a fort from a team of attackers. And the second one is a half-field offense domain, which is basically soccer domain, where you have an offense team scoring against a defense team. So the idea behind ad hoc teamwork is that the agents in these domains, they have limited prior knowledge of each other. They can have different representations and may have no experience working as a team before. So the domains itself can contain a lot of uncertainty. It can be fully or partially observable with or without restricted communication. So this is actually representative of many practical applications in robotics, like disaster rescue, surveillance, space exploration missions, where you have humans and robots who need to work together towards a common goal. So the agents, they have to learn interactively from whatever they observe, try to understand the behavior of the other agents, and come up with their own actions so that they can achieve the team goal. So actually ad hoc teamwork is a well-established research area. It has been around for at least 15 years. And the earliest approaches, they used to have these encoded protocols or plays to select the actions of the agent. And then it transitioned from that to having 2 main components. The first one is a probabilistic or deep neural network model to estimate the behavior of the other agents in the domain. The other one is to select the actions of the ad hoc agent based on a long history of experiences. So as you can see, these methods are mainly focused on learning approaches, and therefore they are prone to the common limitations like being computationally expensive. So they need large data and resources before producing results. And also because they focus on optimization, it's hard also for them to fully utilize of the common sense domain knowledge in these domains. And on the other hand, because they build these opaque models, they also lack the transparency desired from such systems. So in this work, our inspiration was instead of just looking at this as a learning approach, try to combine knowledge-based reasoning with learning so that they can address each other's drawbacks. So our inspiration lies in cognitive systems, which are in turn inspired by human cognition and control. And in this work, instead of looking at representation, reasoning, learning, acting as very different mechanisms, we want to try to couple them together. So it's not a unified representations, but you have a nice information flow which will sync them together. So you can replace some of the components if you need it without changing the whole architecture. And then, of course, we want to combine the knowledge base with data-driven learning. And to provide the desired transparency, we want the agent to be able to provide relation descriptions of decisions and beliefs. And we want them to be provided on demand to different type of questions. And finally, we also want the architecture or the agent to be able to incrementally learn previously unknown axioms. So this is an overview of the architecture. So if I take the fort attack domain that we saw before, the ad hoc agent can be a guard type agent. And in that case, its teammates are going to be the other guards and the opponents are going to be the attackers. So the agent is going to learn models of these teammates and opponent, and it needs to do this on the fly with limited data. because it's ad hoc teamwork domains. So because it has these behavior models of the agent, it only needs to have minimal declarative knowledge in its knowledge base. And at the same time, it's going to continuously receive observations from the environment, which it will use to revise these models or learn new models based on the data. And the axiom learning component is used by the agent to incrementally learn new axioms or acquire new knowledge. And the explanation generator component is used by to create relation descriptions as answers or explanations to different type of questions on demand. So in this presentation, I will mainly focus on the explanation generation and axiom induction. But for the completeness of the presentation, I will also briefly go through the other components. So the knowledge representation and reasoning component, we use an action language to describe the common sense knowledge of the world. So it has a system description which consists of a signature and set of axioms. So the signature has statics, which are actually the attributes that cannot be directly changed by the actions of the agent, like next to here, which talk about the relative arrangement of places in the domain. And then it has fluence, which are actually the attributes that can be directly changed by the actions of the agent, like the location of the agent. And then we have the actions of the agent, like moving, shooting, and things like that in the phototype domain. We also have mainly three types of axioms. The first one is a causal law, which says that moving to a place make the agent to be in that place. The second one is a state constraint, which says that the agent cannot face two directions at the same time. The third one is an executability condition, which says that it's impossible for it try to prevent the agent from trying to consider a shooting action if there are no attacker agents in its shooting range. So apart from this, the agent also has a partial history, which consists of prior observations, the action executions, and some initial state defaults. And the agent can do the common reasoning tasks like planning, diagnostic, and inference. And to do that, we use answer set product because it supports the non-monotonic revision, which is really important in this kind of uncertain domains because it allows the agent to revise previously held conclusions. So then the agent can prioritize different goals at different times because the agent need to consider both team goals as well as its own goals. So for example, in the fort attack domain, if it sees an attacker who's near the fort, then it can prioritize to shoot that attacker. But otherwise, it can also decide to spread around the fort, trying to maximize the security of the fort. And also, we use the optimization statements in Klingo to minimize the total cost when computed in the action sequences of the agent. And finally, another important aspect is the use of refinement and zooming. So we adapt on previous work to use the refinement and zooming here because it allows the architecture to be scalable to much larger and complex domain with many agents. So basically, for example, in the fort attack domain, if the agent sees an attacker and it needs to shoot the attacker, then it needs to know exactly where the attack agent is in. So in this case, it needs to reason in the final resolution. But if it only needs to know a general idea of the location of the agent, then it can do in the Cosa resolution. So at each step, it can reason in the Cosa resolution and decide whether it wants to zoom into the final resolution or not. And then this is again a brief touch on the predictive behavior models. So having only this knowledge is not sufficient in ad hoc teamwork because the domain itself and the behavior of the agents can change over time. So because of that, we use ecological rationality approach to create the predictive behavior models. So these behavior models need to be learned on the fly with limited data. So ecological rationality focuses on adaptive satisficing, where it characterizes the behavior as a function of both cognition and the environment. And then we use algorithmic model of heuristics so that we can ignore part of the information from the observation to make decisions more quickly and accurately. So by doing that, we have decided to learn a set of fast and frugal decision trees. And here you can see part of the trees that was created for a guard type agent. And as you can see, they have limited spread and depth, and it is easy to interpret by the humans. So when come to the transparency, instead of actually trying to describe all the decisions made by the agent or try to make the whole learned model interpretable, what we try to do is we try to identify the axioms and literals that affect the agent to take that action or belief, and then try to create relation descriptions as on-demand explanations. So we type basically 4 types of questions. The first one is action justification questions, where we ask the agent why it decided to include a particular action in its plan, or it decided to execute a particular action. And the second one is contrastive questions, where we ask the agent why it did not do a particular action. The third one is belief justification, where we question the agent about the beliefs that it has particular time steps. The last one is counterfactuals, where we question the agent about hypothetical actions, which considering its own actions as well as the actions in the other agents in the domain. So when we created the architecture, we deployed it in the fault attack and the half-field offense domain that we described before. So here we have the accuracy of the predictive behavior models that we created using the fast centrifugal trees. So you can see that they have considerable accuracies, and what's important is that we were able to come up with these accuracies with much smaller data when compared with the state of the art based on data driven approaches. So for example, in the fault attack domain, we only use 10,000 examples, where the state of the art use millions of data. And then, so it is important in ad hoc teamwork that the agent is able to adapt to new teammates that it has never seen before and react to the behaviors in the environment that it has never seen before. So because of that, we trained the agent with a different set of policies, but we tested it with some policies that it has never seen before, and these policies were based on sophisticated systems like deep neural networks. And we were able to see that incrementally the agent can actually adapt to these new agents while also revising the models that it has and also learning new models, and it can do this on the fly. So here we have some of the results that we got from the half-field offense domain. We also have same results from the similar results from fault attack domain, which we have included in our paper. So the first bar in blue color is actually the proposed architecture, and the second one is interesting because it's where you have only the logical reasoning component of the architecture, where we don't use the learning component. And so you can see that the combination of both can actually perform better than just having a single component. And the other two are actually well-known state-of-the-art methods in ad hoc teamwork, which are mainly focused on deep neural networks. So we have 2 sets of bars here because in the first one we have 2 offense agents playing against 2 defense agents, but in the second one we have 4 offense players playing against 5 defense agents. So you can see that when the environment becomes complex, the logical reasoning based architectures can actually perform better than the data driven architectures. So when it comes to axiom learning, what we did was we allowed the agent to select an action and execute in different initial states that is created by the program. So then we collected the data of the unexpected literals and the literals that is supposed to be there but which are not observed, and then we used that data to create a decision tree. So here you can see part of the trees that was created for a learning and executability condition. You can see the executability condition here, which says that the agent cannot shoot if it doesn't have the ball. So the agent follows the path which is in gray color to create this executability condition. And we also recorded the precision and recall of learning these axioms. And also in the half-field offense environment, we deploy the agent with and without these learned axioms. And we were able to see that when the agent runs in the environment with these learned axioms, it can actually perform better than without the axioms. So for the transparency or the explanation, I have included some of the execution examples from the photo tag domain. So the first one is an example for an action justification question where we ask the agent why did it decided to move to this particular grid cell in step 4. So here the answer of the agent is that because the attacker was not in range for shooting. So basically the agent here starts, the ad hoc agent is the agent in green color who start from 313, and it's trying to, the overall goal of the agent is to shoot the attacker who is in red color. So it decided to move to 713 and shoot. So the question is about why it decided to move to this step. And the second one is an example for a contrastive question where we ask the agent why it did not decide to move the attacker in a step before. And here the answer is because the attacker was not in shooting range at step 2 as it moved toward fort in step 0 and 1. So here the agent tried to identify the active literals and the executability or preconditions that prevent it from doing the shooting action, and it come up with this explanation. And also it used the output from the behavior models to take into consideration that the agent was supposed to move in step 0 and 1. And finally, so we also have the belief justification question, which is why did you believe the attacker was in shooting range? So here the answer is that it observed the attacker was in this location and the also the location of the ad hoc agent and the orientation. So if you keep on asking questions about this state, it can also give you the more details about how it calculates the shooting range and what information has been used. And the counterfactual question is where you ask what do you think the attacker 1 will do in step 2. So here we can ask questions from the agent about its own actions as well as the actions of the other agents in the domain. So here the agent says that it thinks that the attacker 1 will move up since all the attackers are alive and the attacker 1 is in front of the fort. So it used the behavior model to hypothetically think a few actions forward and come up with the answer that it thinks it will move forward. And it used the transparency of the fast and frugal trees to come up with the explanation. So to summarize, the contribution of this work is an architecture for ad hoc teamwork which combines non-monotonic logical reasoning, probabilistic reasoning and interactive learning where they inform and guide each other. And then we have a clear separation of concerns. So each of these components can be easily replaced by others. So it is not something that is applicable for these two domains, but it's a common methodology. And we use stepwise refinement which allow us to scale this to much larger and complex domains. We use ecological rationality for much reliable and efficient reasoning and learning. And we also provide interactive explanations of the agents which are constructed on demand. And the agent is also able to learn previously unknown causal laws and executability conditions. We are also working on the state constraints at the moment. So, thank you. Any questions?
Questions?
Yeah, so I had a question about the nature of justifications. So you asked the agents to justify the actions they took, and the system generates the explanation at the time you ask them. Is it also true that that justification was why they took the action? So the justification the system produces is an explanation for the action, but is it necessarily true that that is the reason why the agent took the action?
So you mean by there can be multiple explanations? Yeah, it is possible that it can have multiple explanations, but in this case, so we don't have a method at the moment to prioritize which is the most important axioms. Instead, what we do is we take all the possible explanations and we give them as answers. And for future work, we also need to prioritize, like for sometimes we have multiple state constraints which can be doing the same action. So in that case, we have to prioritize which is which.
Okay, yeah, I was just thinking about how there's kind of a parallel with human explanation justification, which is, according to psychologists, we don't come up with justifications until after we've made a decision about what to do.
Yeah. Human, yeah.
Other questions?
Just a quick one. When you gave statistics of the accuracy of the agents you were training, what would 100% mean? Not on that one. A few slides earlier.
Oh, this one.
Yeah. What would 100% mean? What were you measuring it against?
So 100% would mean that we can, the behavior model can accurately predict all the actions of the agent. So it actually doesn't give you 100% because there are some deviations from what it actually does. So to improve the accuracy, what we do is when we see a different behavior, we try to revise the model. Yeah.
So can you tell us a little bit about the fourth attack and field offense, half field offense, tokens?
So actually the fort attack is like a team of guards who are trying to, the first one, a team of guards who are trying to protect a fort from a team of attackers. So you have two teams, an attacker team and a guard team, and half-field offense is a soccer domain. You have an offense team and a defense team, and they are trying to score goal against each other.
So there's a question of how generalizable are these techniques because they very specific domains.
Yeah, I think so. When I was doing this, I was able to apply most of the axioms that I learned from the other one, the fort attack, for the half-field offense domain. And I think the most important thing is that we can actually, so the mostly difficult part to replace is the learning part. But in that case, because they can be learned on the fly, actually with limited data, so they can be replaced real quickly. But for the axioms, we use most of the axioms in the same domains to the other domain.
And what you learn is what, an answer set program or something, some kind of rule? What are you learning? Yeah.
We are learning the constraints actually. So in this one, I mainly use executability conditions and quotient law, learning quotient law and executability conditions.
Other questions? Comments? I'm curious whether have you already tried it or are you willing to test your framework with physical robots or real situation, let's say?
Actually, it's in progress. So we are currently trying it with some physical robots, mainly turtle bots. So it's in progress. Probably I'll be able to provide something this year.
Thank you. Okay. Thank you. Let's thank again the speaker.